First, yes, thanks, Nassim. So first, this is not a virtual background. This is actually, let's say, whatever remains from the KAPPA office. So, I mean, the good thing is that they have put electricity back, which is great. And also, I have to say, I still have a test life. This is now the name of the donkeys that you see here. So let me just try to get to the next slide, if I can. Yes. Well, thank you for attending. The goal of this webinar is to introduce you with the work that we have been doing in the past 4 years or so on automation, even though I will also use this occasion to introduce you with a sort of very progressive migration that we are undertaking on Generation 6. But first, a reminder of what KAPPA does. So the perimeter of what KAPPA does today is what we call the analysis of dynamic data. So the principle being that whenever there is a movement of fluid within a reservoir, within a well, between wells, or even now within a PVT cell actually, and whenever there are some data recorded in response of this fluid movement, whether it is rates, pressures, volumes, temperature, and whatever raw signal, then depending on the context, we will have some analysis techniques that are basically industry standards that will be used to calculate some results and take some operational decisions. And also, in most cases, we will try to use a model, which is a proxy of the system that we are dealing with, which so it could be a straight line on the right scale, it could be an analytical model, it could be a numerical model, it could be an equation of state. But we will use this model to match the data that we have acquired. And then in most cases, we will also use it to forecast, to project ourselves in the future and forecast what can be happening. So this is what KAPPA does basically through its different software products. And we do that, so we have been doing that in two additional contexts that are more recent basically than KAPPA. The first context is what we called intelligent fields 20 years ago. And this is this context that is getting us to the automation work that I will be presenting now, and Olivier later. And the second context, which is like from 10 years ago, is of course unconventional resources, which is something that we have put a little bit on the back burner this year for obvious reasons. So to implement all these things, we have developed in time a certain number of engineering applications, some of them you may be using, which I will not detail here. But the idea, the main idea is that whatever the workflow, which generally have been developed starting in the 1950s, all the workflow we have been using are based on the assumption that the engineer needs to understand the physics of the systems that he or she is dealing with. And historically, at least to grow this understanding, we had to to undertake some specific operations, like a well test, that would allow us to get data to increase this understanding. And these operations would typically involve risk and cost that you would have to mitigate with the value of the information that you are looking for. Now, so the name of the game was that we wanted to add in permanence pieces of the puzzle so that we grow our understanding of the systems. Now, in terms of software, because this is what we are doing, especially since the mid-80s with the development of the spread of PCs and the early 90s with the development of Windows as a sort of standard OS for this sort of thing, the software that was developed, KAPPA or otherwise, was based on a human interaction because the engineer would be the one doing the whole thing from the load of the first data to the final analysis. Regarding artificial intelligence, there was a hype actually in the early 90s, and we have been playing a little bit with it, especially Olivier Allain. And the outcome was that it was nice, it was fun, but it was certainly not a serious contender to take a substantial part of the workflow. So we kind of gave up on it, on that, something like 20 years ago. In terms of now, automation itself, which is different from artificial intelligence, didn't start for us 3 or 4 years ago. It started around 20 years ago. And just for KAPPA, I kind of arbitrarily set 3 years that were kind of a breakthrough for us. that I'm going to detail. So first, 20 years ago was initial release of and deployment of permanent gauges in the Gulf of Mexico, and then it quickly spread worldwide. And this was the first time where we faced, as reservoir and production engineers, the notion of data overload. So this data was great because at the same time, so first of all, there was no need of a specific operation. The data was there, so this means that it was just a matter of taking the effort of using them. But this data would include some, I would say, high-frequency events like shut-ins that would act like a free well test. And the rest would be low-frequency information, so that like the producing pressures. So the high-frequency events could be used typically in SAFI for PTA, while the low-frequency production could be used for RTA that was developing at this time, or even history matching. So it was great, except that if you take high frequency over a long period, you get basically too many data. So at this point, the challenge was to develop algorithms that would allow to, say, to reduce the number of points by a factor of 100 or 1,000 without creating too much entropy, so without losing too much information. And so we implemented some algorithm that was acting as a high-pass filter whenever there would be a shut-in and a low-pass filter for the rest. And it was reasonably successful until basically we got to the limit of that, and that was a few years later, when with the spread of permanent measurements all over the place, and the fact also that each engineer was getting the responsibility of more and more wells, we ended up with another overload that was information overload. Too many things were happening in the reservoir, and in fact, the engineer didn't have time to do a proper process for each well. So then the challenge at this time was to help the engineer by identifying events of interest, eventually cleaning up a little bit the data so that the data would be ready for analysis, and then send a notification to the engineer that something was happening at this well, and basically on a single click, he or she would be able to run analysis if there was interest. And so the outcome of this two-stage automation that was pretty basic, but actually required some investment on our side, was what is KAPPA Server today, which is basically the client-server application that is being deployed now within many operators. So KAPPA Server was a client-server application working, is a client-server application working 24/7, and that is doing in series a certain number of operations: mirroring, filtering, correction to datum, identification of events, and cleaning. The goal being to send the resulting data either to Sapphire or Topaz for analysis, or to a database where it could be used by a third party. And then the third phase of automation stroke, and this happened in 2016. So of course, as you recall, this was the time of our first crisis now, I mean, at least first recent crisis. But actually, even though probably it sped up the process, it had to happen no matter what, because the operators that were using our systems got back to us to say, still, okay, it's nice, but it's not good enough. Engineers are still wasting too much time on repetitive tasks. And basically, with all the sophistication of processes that we can have today, we want that most, if not all, these repetitive tasks to be automated, and maybe even more sophisticated things if possible. So that was a basic request from our users, I would say, irrespective of the crisis that was looming. But also there was a technology opportunity, so they asked us, well, by the way, can we use this sort of recent cool stuff on AI and data analysis? By the way, we are, let's say, now getting virtual, so we need to have this thing deployed on cloud. And by the way, you know, whenever you have a handheld device, a smartphone or a tablet, well, we would love to have bits and pieces of this workflow implemented on these things. And the underlying question was, is this next generation about still improving the existing workflow? The answer is yes. Or is it about creating new workflows that will basically flush whatever we have been doing in the past? So 3-4 years ago, we had a perfect storm of a combination of, let's say, human context and technology context. The human context was not so great, actually, because first of all, we had what we call the big crew change. So, I mean, the funny thing is that in 2015, the big crew change was the main concern of SPE, you know, so the times change. And this came from the fact that we had this original scene, may I say, in the mid-80s, with the first oil crisis, where the industry failed to keep on hiring young engineers and induced a demographic gap in our engineer population. I just want to make actually a parenthesis here. You know, KAPPA was created in 1987 by Dominique Bordet and myself. Olivier Allain came a couple of years later. And I can tell you, so that was the first crisis. And I can tell you that everybody, including myself, agreed that it was the worst possible time to start a business. In retrospect, it was the best possible time. So just to, well, okay, we are in a hard time now, but you know, we will get through it. We actually, as the Chinese and also Kevin love to say, you know, threats are also opportunities. And again, obviously, whatever doesn't kill us will get us stronger. So basically, we'll get through it. But anyway, times are fine. So you can see my, let's say, the KAPPA office behind. But the second context is also something that we call the crisis 4 years ago. Now we have to say that we have a double dip. So it's 2015 and 2020 crisis. So thank you very much. And this is basically the context where effectively we are going to have less engineers. We are going to have engineers with a lower average experience. So automation, of course, has its role to kind of partially mitigate this problem. And then we have, sorry, the technology context, which is actually a little bit positive. So handheld devices, cloud deployment, and also this sort of hot buzzwords on data analytics and artificial intelligence. I'm actually going to make a small parenthesis on AI. And by the way, I'm not an expert on this. So basically, whatever you read here is whatever I know. But you know, after the disillusion of the early 90s, there was this challenge in 2012, so 8 years ago, where essentially, you know, a bunch of bitmaps and photographs were released, and the challenge was to be able to have AI systems that would rightly identify what it was about. And at this time, the best score was around 74%, and very quickly it got to 84%, and a couple of 3 years later to 96% in terms of success rate. And this is where basically the new hype started. Now, AI is a sort of, artificial intelligence is a sort of onion. You know, you have several classes and subclasses and subclasses. So speaking about what we are dealing with today, so in AI, there are several classes. And what seems to be hot today is what we call machine learning, which is essentially a system where the performance of the system is supposed to improve while the system keeps on training on new data. Within machine learning, there are also several alternatives, and deep learning seems to have the edge. So deep learning is essentially about neural networks. And within neural networks, basically, convolution neural networks are the ones that are popular so far. So it's not exclusive, but it seems to be the things that we are going to work on. To finish on AI, so first of all, you know, there have been some sort of controversy about artificial intelligence. Now, really, you can name it what you want. You can name it artificial intelligence, so it looks like Star Trek, and it can be a bit, let's say, misleading. You can get to the point and speak about convolution neural network, which is technically what these algorithms are about. Or if you want to basically humiliate the process, you can call it a glorified least square, and well, this is your choice. But there are two things. The first one is that there are certainly game changers. What I mean is that there is no doubt that this algorithm will have a larger and larger importance in the workflows that we are going to use in the years to come. But there is a limitation. And in fact, last year, the same consortium that started all published a certain number of pictures that were natural pictures. They had not been edited to fool the system. And on these pictures, basically, the systems that had been so successful and started all, basically, were pathetically failing. First, they couldn't identify the right thing, but also they were identifying the wrong thing with a degree of certainty that would make you think that it was sure of its thing. So, for example, this poor squirrel would be identified as a sea lion with 99% certainty. Now, naturally, you could train even more, and ultimately these images would become, let's say, part of the training and would identify the thing correctly. But the underlying conclusion is that wherever this nice algorithm will go, so far, we may be proven wrong, they cannot get to 100%, which means that they are not really a candidate to replace the engineer at the top of the decision tree. And this is, I think, an important thing for the things that are coming. Now, going back to what we have today with KAPPA Server. So KAPPA Server is actually, we are very proud of it, but essentially it's a kind of monolithic application. First of all, it's built 100% by KAPPA. It has limited opening. It is doing in sequence a certain number of predefined processes. And its main goal is essentially to feed, say, data to KAPPA Software. And it would be installed on one single machine. It could be a virtual machine, but it would be on one single machine. So if we look at the work that we are doing on automation today, it is totally the opposite. We are, so Automate, as it's going to be deployed in the months to come, is actually totally decentralized. And the main information here is that we have taken the option, which actually most of the technical groups that are working on that have taken, which is to switch from rich monolithic applications to what we call microservices. A microservice is a piece of software that is basically big enough to do something substantial, small enough to not to be the gas factory that is doing everything, and independent in that state, in that sense that it will be listened to whatever is happening, will pick the information that is relevant to it, will do its part of the work, and then push the result of its work to basically the common point. And so the idea here is that all these microservices that you are seeing with these little circles all around can be installed virtually anywhere. They can be installed on a single machine, even though we need Windows and a Linux operating system. But they could be installed on several machines on a network, or installed on different virtual machines on the cloud, or any combination of this. The only condition is that they have to see each other via TCP/IP, and they have to connect to a sort of orchestrators that will allow them to speak to each other. Now, I'm going to kind of go to bits and pieces of this slide. First, speaking about the architecture, so the thing that is allowing the whole thing to work. And of course, the components that I am showing here, which are either microservices or servers, have definitely not been developed by KAPPA. This would be beyond what we can do. They have been either developed or they are being used by IT giants. And this is a good news, because this means that these things that we are using have been sized to do things that are, let's say, 1,000 times or 1,000,000 times what we need them for. So we are pretty sure that these components will not fall on us. We may be short of hardware or virtual hardware, but these things will certainly follow the growth of our needs. So most of them are Linux-based. They are open source, except Kubernetes, which is an orchestrator that has to speak to both worlds. Now, in terms of KAPPA Server, so the things that I was showing before, that is what we are using today. Well, you can see that in this in a part of the schematic. So you see on the bottom left a traditional computer with a human being behind it, with Sapphire, Topaz, Ruby, or the other software, which will of course go and pick data from the system and eventually push models into the system that could be taken over by AI systems. And then you see the 4 components of the PDG processing. So 2 of them are, let's say, microservices, and 2 of them are, well, something a little bit below, the service that is called processing. Sorry. So then, in complement of that, we have other microservices that we have developed, but probably the interesting part is on the left, where you see the PTA, the RTA, and the numerical. And these are essentially Sapphire, Topaz, Ruby, minus the user interface, plus lots of APIs and protocols that will allow a third-party application, including an AI system, if needed, to execute all the steps of the workflow as a sort of alternative of what the engineer is doing. And then we have, let's say, the way, because again, as I was saying, KAPPA Server was essentially a closed system, at least compared to what we can do now. And here you have the 5 different ways engineer, the IT or the R&D center of an operator, a third-party application developer, or ourselves actually, could customize the workflows. So on the bottom, you see the things that are built in Automate. So you have functions, which are basically something like Excel, an Excel equation that you would program on a cell, a little bit more sophisticated that you could use to make simple transformation of your time series into something else. And then you have something that is quite more powerful, which is what we call a user task, that will allow you to program in C# or Python for the time being. Well, anything you want. So first, maybe to test some workflows before it becomes a full microservice, or even to call as a slave libraries that, especially the Python libraries, give you enormous potential, or even a third-party application, as long as there is a protocol that the user task can pick. And then on the top, you have whatever could be developed by third parties or operators. These could be applications, a bit like KAPPA-Workstation, or this could be also microservices. And I have arbitrarily split them into data analytics algorithms that would be used to access time series and constants or whatever, and get something out of it. AI system, whatever they represent, and then anything else that I would call deterministic workflows, whether it is Monte Carlo analysis, regressions, or let's say anything that you could effectively program in a standard way. Now, in terms of deployment, and I will not insist too much on that, you will need to have a certain number of virtual machines, again, either on physical machines or on the cloud. Typically, you will need a minimum of 1 Windows and 1 Linux, but if you want to have all the backup and high availability solutions, you will typically go for 5 machines, 2 Windows and 3 Linux, so that basically, if one of them fails, they will be able to go on without any substantial drop of performance. Now, what I've been showing here is essentially Automate as a sort of standalone solution. This may be the case, but when we anticipate that for most operators, KAPPA-Automate will only be part of the picture. So we see that KAPPA-Automate potentially also as a satellite of something that would be much bigger. The advantage is that because most developments today are using the same technology component, this means that when you install a KAPPA-Automate in an existing environment, whatever exists would not need to be installed again, and they basically would be connecting to our database and Cassandra and you name it. Also, what is important is that we have, there has been a sort of consortium, initiative called OSDU, which are grouping now a large number of operators and service providers. And this is a great opportunity because this will allow us to, very early in the development process, to interface with other software vendors in order to offer so not only a standalone solution, but also a solution that will be plugged to other environments. Just for those who are familiar with OSDU, the 2 first releases of OSDU were kind of irrelevant to us, but with the 3rd release, where you will have the involvement of Delphi that was donated by Schlumberger, we will start to have access to time series, etc., and we will be able to test automate in an environment that is relevant to what it's going to do. Last slide on let's say on last philosophical slide. So you see on the left part essentially what we have today. So a human being that is using KAPPA server to have a PDG data pre-processed and KAPPA-Workstation to do whatever analysis. So you see on the right the counterpart with KAPPA-Automate, which is actually grouping everything, what KAPPA server and KAPPA-Workstation used to do, but of course, only from a point of view of automation. And naturally, down the line, we could imagine that KAPPA-Automate could be operated by some Spark process, which right now we don't have the beginning of a beginning. But in any case, so whether, let's say, the KAPPA-Automate is a standalone or controlled by some kind of AI, we believe that there will always be a human being, basically, that will either control the process or control the AI. Now, in terms of the user interface, so we are going to have a demonstration a little later by Olivier. So we wanted to be adaptive to all kind of devices. So this led us to replace our Windows environment by a web-based environment. So basically replace rich clients by a web with an adaptive way. So this means that the system will adapt to the size of the device is still dealing with, and depending on the context, it will allow this or this to be accessible by this device. Then, as I said, I'm going to make a very short parenthesis on software generation. I'm not going to bother you with the detail, but just to look at so what we have today, and you have had this Learn Something New presentation on Generation 5. Our current software portfolio is essentially about Generation 5. This Generation 5 was initially released on 2016. And there's something that we have learned, basically to our detriment, is that unlike the previous generations, where it was taking basically 1 year or 2 years to switch from one generation to the next, the move from Generation 4 to Generation 5 was pretty painful and long. And it's only now, 5 years after, basically, that we are now starting to phase out. Let's say we have had more than 80% replacement of Generation 4. And I want to believe that it's not that we did something very wrong, but essentially at the time of crisis, people had other things to do than just learning a new environment. And as long as the software they were using was fine, they were kind of putting the move to Generation 5 in the much too difficult trade. So even though we have started to work on the 6th generation, we are not going to start working on a Generation 6 migration to Sapphire, Topaz, Ruby, etc. for 2 reasons. The first one is that it has been painful enough. We want to have our users digest Generation 5 before starting to tell them that they need to relearn again. And the second also is that even though the work on web-based application has been substantial and really what we can do now with web-based applications is really remarkable, it's still not quite as friendly and as powerful as what you can have in a rich application, in a Windows application. So in a software like Sapphire, we would lose a bit now if we were moving to Generation 6 now. So anyway, this is ultimately the way to go. And this is just to show you that how busy we have been in the past 30 years in terms of new versions and new generation. No, actually the interesting thing is at the bottom right, where you see in blue where we are going into the 6th generation. So obviously KAPPA-Automate, which will be released next year, will be a 6th generation in terms of user interface. And we are releasing, actually we have been releasing a couple of weeks ago, our first Generation 6 application, and maybe the last one for quite a while, which is a fluid modeling tool that allows us basically to move from PVT experiments to an equation of state. This actually will be the subject of a separate webinar, so I will not go into the details, but what is interesting with this Generation 6 is that when you have a web-based application, you can actually package it in a sort of pseudo Windows application, so you can use it the good old way as a standalone application on your laptop. But you can, of course, because it's web-based, use it as a client server. And of course, in the context of KAPPA-Automate, you can use it as you will be able to use the number crunching part and the workflow part within the microservice of KAPPA-Automate. So I will finish my presentation on just presenting a consortium, and nothing to sell here, with whom we have been working on the development of automation. So it has been joined by a certain number, so we have 13 members now who are all operating companies. And we started 4 years ago, and when we started, the first thing we wanted from our members was that they tell us their story. So which means that irrespective of the technology, irrespective of what can be done now or in a few years' time, is how do you see the work of your engineers in 4 or 5 years' time? And tell us basically your story. We actually built our own story too. And we also use these initial years to choose the architecture and the technology that we would select to develop this project, except that this technology is evolving so fast that there are some architectural choice or technology choice we took 4 years ago that we had to crash last year or 2 years ago because it is evolving so fast. You know, you just need an announcement by Microsoft on something, and then basically it questions everything we have been doing. So it's a bit challenging, but it's basically the price to pay to be a bit at the edge of what development is. So we also took these 3 additional years to develop a proof of concept that we are going to, that Olivier is going to demonstrate to you now. And also we took this occasion to make sure that this POC would be, we could deploy it both on an intranet or in a cloud environment. We also took this occasion to convert Sapphire, Topaz, and Ruby into microservices. Ultimately, when we get to generation 6, we will probably split the things into smaller microservices. This is a little bit, Sapphire is a little bit big for a microservice, but okay, this is what we had to do temporarily. And of course, we wanted to reproduce all the capabilities of KAPPA Server in this proof of concept. And finally, we implemented the first stories that we want to implement so that we can show you something new, basically, today. So this ended up, let's say, actually, we are not completely finished. So in 2020, in a couple of months, we will finish with, we will promote the proof of concept to what is called the minimum viable product. And this will get us to the second phase of the consortium, where some of the members will allow us to deploy the Automate prototype into their operational environment. I mean, we didn't want just to have them install that on one machine on the side and play with two sets of data and say it's fine. We really wanted to have the thing tested on scale 1, on the number of hundreds of wells or thousands of wells that they are dealing with on a daily basis. So of course, to do that, we needed to have a non-intrusive installation, because if we get into the environment, we just don't want to have a prototype killing everything. And again, we also wanted to validate that the deployment could work in a cloud environment. We wanted both to test the KAPPA stories that Olivier is going to present, and also start implementing the stories that operators had told us 4 or 5 years ago. And the goal, so even though the consortium will finish by the end of 2022, the goal is to have a first commercial release of Automate by the end of next year. So again, as I said, the name of the game was that Automate would not touch anything, basically. KAPPA Server would send, whenever it has time, the data and all the data it has to KAPPA-Automate, and Automate would commit not to write anything in KAPPA Server, not to try to access the data historians at the risk of affecting the performance of the system. And this is the end of my, so I'm almost on holidays now. This is the end of my presentation, and Olivier will take over the second and last part of the presentation. Just one thing, Nassim, unless you think that there are some questions that need absolutely to be answered now, I would prefer to have them at the end, but again, you are the judge of that.
Sure, thank you, Olivier. Yes, thanks for a great presentation there. And so far, I think we can save the questions until the end. I think it will be best to do that, because actually the questions, I'm sure, will be answered once Olivier starts.
Yes, that's what I was expecting.
Absolutely. So I think it's best that we let Olivier present the live demos, and hopefully the questions will, if they're not answered, I can always ask them at the end of the session.
Okay, yeah, I will have a talk. Okay, so I'm mute myself.
Thank you. Perfect, great, thanks.
Okay, great. So Olivier, can you stop sharing then? Thanks. So let me take over just a second. Okay, do you see my screen?
Yes.
Yes, okay. Okay, so
yes Olivier,
sorry? Okay, it's fine then, huh?
You can see your screen, so we're good,
Okay, very good, thanks.
Perfect,
right, so,
okay, go ahead.
So I'm going to talk about the big stories and in the demo illustrate some of them. So let me skip the bullet list here and I will go through them one by one. So Olivier mentioned this before, but there are a number of ways that you can extend the functionality of the platform. So the most basic one is the function, which again, I mean, for the KAPPA server users is a bit like the direct channel. There is the second way, which is more powerful, which is the user task, in which you basically define a task by a script. So right now we're supporting C# or Python, but actually we can this can be extended. And there is also a third way that you can customize the system, which is in the data model. If you want, KAPPA-AUTOMATE is extremely loose in the typing of properties or the typing of data. But you can use well properties or data types as a way to basically automate some replication or some action from one well to others. The other way in which let's say the system is open is that all the microservices of KAPPA-AUTOMATE are accessible. So it is possible to query at any point in time microservice to get information from it. It's possible to use the function of a particular service. And it's also possible to tap into the events, so basically what is driving the workflow on the platform, and to react to those events by new processing or to add new processing and send new events to the platform. In terms of the implementation itself, so I mean, for those of you familiar with the web technology, this won't be anything new. So we are using a REST API for all the microservices. They all work with, let's say, a message that is sent in a format called JSON, which is some basically a markup language. All services expose their API, and this API can be seen quite simply with a tool like Swagger, which I will demonstrate later. And not only can you see it, but you can also test the API live. So it's a very good way of actually interacting and discovering the function of the platform. And of course, access to the API is restricted and secured using standard authentication like OpenID and so forth. Anything, so once again, anything that happens on the platform is happening because of events, and any action is sending event. So all services cooperate through event, and we use for the backbone something called RabbitMQ. And it's possible to tap into RabbitMQ, so this is possible in particular through the SDK. And then you can react to the existing events, which are all, let's say, defined by, let's say, organized by topic. So there is like a dictionary of events that tells you exactly what the events are, what they correspond to, and so on. We have developed on top of the platform Python SDK. So essentially what this SDK does, I mean, the core of it, it's the Python implementation of a facade to the REST API of the various services. So it allows to use the REST API, but through some Python code for any of the platform services. It allows obviously to connect to a server, and it also allows connection to the bus and listening to the events and subscribing to particular events. One of the workflow that I will demonstrate later, and that we call our, let's say, proof of concept number one, leveraging the SDK, is a workflow where, I mean, it's a static workflow here. The idea is that within KAPPA-AUTOMATE, so under well, you have a number of documents containing some, let's say, PTA data with a number of extractive buildup. And what we do is that from the Python code, we ask KAPPA-AUTOMATE to provide the document. So this is step one here in the workflow. We use the Sapphire application that is on the backend to extract from this document test parameters, so RW, H, porosity, and so forth. We also ask the Sapphire instance to provide the log. And then from those log, we do processing, which is essentially to look for infinite acting radial flow here. It could be other flow regimes. And we do this, I mean, the whole workflow was inspired by some paper by ExxonMobil a couple of years ago. And once we have those, this infinite acting radial flow estimate, we get essentially time series reflecting skin as a function of time and KH as a function of time. And we write those back to KAPPA-AUTOMATE. So it's a one-shot workflow here that I will demonstrate later, and that can be developed very simply through the Python SDK. The second proof of concept that we are completing now, you will not see it today, but I mean it's almost completed, is basically the same thing, but done recurrently as new shut-in are detected. So on the first line, you see, for instance, a state in which two shut-ins were found. We have let's say, microservices encapsulating this Python code that has identified the first two infinite acting radial flow on the first two shut-in. And when a new shut-in is detected, essentially the new microservice is reacting to the event saying a shut-in has been detected, and is making the computation to get the new infinite acting radial flow and sending back KH and skin. So in this mode, basically, as the data is progressing, KH and skin will be fed back to the platform. The third proof of concept that we have started to work on is one that we call incremental PTA. So the main idea here is that at a given point in time on some existing shut-in, an engineer has made a PTA analysis, so that's the top line, and this analysis ended up with a model match that we see on the top right-hand side. The document is uploaded on the platform, and from that point on, what we want the system to do is essentially, as soon as a shut-in is detected, first to regenerate the model on the new, so to extract the new shut-in, to regenerate the model, to report the error between the model and the data. That's the first information. And then second, to regress on the model to try and fit the model on the new shut-in, possibly not allowing, let's say, a change of all parameters, but selecting only a few. We have actually included within Sapphire a wide search algorithm, which, I mean, we used to have something like this in ECRA with genetic algorithm and gradient-based optimization. The new one is using a differential evolution coupled to gradient-based optimization. So this is again a workflow that we are currently completing. We have done a number of other things using Python and using the Python SDK. Now, as you know, around Python, there is a very large ecosystem of scientific libraries or let's say machine learning data analysis libraries. We have used here two things. So on the left is something pretty simple for outlier removal that we trialed as an experiment. What's on the right is a bit more interesting. For those of you familiar with Topaz, in Topaz we have a deconvolution which is called feature-based deconvolution, which amounts to basically trying to find the deconvolution as a combination of simple feature curves, which correspond more or less to, let's say, the basic flow regimes. So the idea here is that as the data is coming in, we have a system that tries to run this feature-based deconvolution. So it's a bit like learning how to predict the pressure from the rates and changing the model as time goes. So there are two interests to this workflow. The first one is to identify major changes in trend and to flag the user when they happen. So that's step one. And the second interest is that through the process, you get a deconvolution response, which is shown at the bottom, which can be an ideal candidate for some kind of PTA analysis, at least, let's say, in single well environment, when, let's say, interferences between the wells is not too strong. So that's let's say some of the other developments. One workflow I will demonstrate later is the virtual meter. So the idea here is that for a given well, we have made one analysis, let's say production analysis using Topaz, and we end up with some kind of model that lets us simulate rates from pressure. And from this point on, what we want is that we want KAPPA-Automate systematically to generate rates from pressure as pressure is progressing. So this can be done on, let's say, single well basis in a green field when no strong interferences is felt between the wells, or if we are in a situation with, let's say, significant interferences, then a single Rubis document could allow virtual metering on a number of wells at once. Another workflow that we have planned to integrate and that was developed originally in the context of Citrine is what we call model mining. So here, the objective is that we have a very large number of wells that need to be history matched and forecast. And of course, I mean, ideally, we would like to do a fine model-based analysis of all of the wells, but this is not achievable. I mean, well, mainly because it would require user interaction and would be far too difficult. So here the idea instead is to have only a few real models generated, which could be actually either the result of, let's say, sorry about this, which could be the result of, let's say, user interaction or Monte Carlo simulation done automatically by the system. And then the name of the game is to try and use those model-based response to match. So we do some kind of combination of those model-based response to match the existing history. And once we have this, then we can forecast the future production. So what we end up with is not a model per se, but it's some kind of combination of real model. Okay, it's insisting. Okay, model mining. The next element, next workflow that we plan to integrate within the platform is to do with DTS processing. So we have currently in Emerald a number of options to deal with DTS data. We have some qualitative interpretation. We also have some quantitative interpretation with temperature model. The point here in KAPPA-Automate would be to bring in all of the data to be able to navigate through the DTS data with time, and when the conditions are right, to be able to trigger automated interpretation workflow. So essentially for inflow profiling, leveraging the engine in Emerald or the engine in Rubis. Actually, we have a thermal proxy and a full transient thermal model in Rubis that could be the candidates here. The last, this is just an illustration of the display in Emerald that would be offered in KAPPA-Automate for the qualitative analysis. The last slide is about DAS, so natural extension after DTS, or let's say as a complement to DTS, would be to integrate also DAS in the same loop, with possibly quantitative processing using speed of sound computation from let's say the raw DAS data. So that's it for the slide. Now, what I will do is I will move into the demo. So let me get rid of my PowerPoint. And now what you should see is my Chrome Explorer with basically the main view of KAPPA-Automate. I'm connected right now on the KAPPA-Automate server, it's physically in the same office where I'm standing, but it's accessible from the outside. I think Olivier, you were planning to connect with your iPad, but I'm not sure. Well, okay, you can show it.
I'm trying to show something, but okay, you have to be confident that yes, I have the same thing on my iPad.
We take your word for it. Okay.
Yes.
So the first thing I can illustrate here is the fact that the interface is reactive. So I will enter debug mode here, pressing F12, which lets me toggle the display to various devices. So I can see, for instance, what the UI would look like on an iPad. I mean, horizontal or, for instance, vertical. I can see what I would get if I had an iPhone. And one of the things that you see is that obviously the display adapts. And also, let's say some components will change their behavior. So for instance, this menu on the left will be slide on an iPhone, while it will be permanent if I am on an iPad or on something wider. So if I close the debug mode and return to the normal mode, you see here the menu is permanent. Another thing that we are doing regarding the UI is that as we progress, we build in the translation, let's say progressively, in not only English, but also Russian, French, Spanish, and Chinese. So I can show you the Chinese. Don't ask me if it's right or wrong, but some of you certainly will be able to tell. Let me return to English. And now what I will do is that I will actually start with a workflow which is pretty much the workflow of KAPPA Server, but to illustrate how it's replicated in KAPPA-AUTOMATE and also show some of the important differences. So I start with a field which was created, which is a very simple one with a single well, production history in that well, and nothing else. So of course, with Automate, we talk about automation dealing with masses of wells, but in the demo, which only step by step in one well, again, the point is to illustrate the basic functionality rather than the replication. So first thing I will do under this well is that I will bring in some pressure data. So I'm connecting to, let's say, a data source in the web, a PyWeb data source. And under this data source, I have a bunch of tags, including a pressure tag, which is, I mean, an example that many of you have seen over and over. This is our good old Écran guided session 1. So 5-second sampling, 6 months of data. So that's 3 million pressure points. So as the mirror is growing, I can now start doing a number of other things. So I can create a filter, and that's the wavelet filter Olivier mentioned in his presentation. I can see a preview of the data. I can select a slice on which I will tune the filter parameter. So I choose something with some significant buildup, where I will be able to tune the parameters of my filter. So we use wavelet-based denoising, and then a simple decimation behind. So I will just stick to the default here and create the filter. Now we said before that you can run from any kind of device, including an iPhone. If I were running on an iPhone, I would certainly not access a big filter like I had for what I just created. But instead, I could use an auto filter option, which would take all the default and essentially create the filter in one.
Yeah. If you want, I may try to make an automatic filter, or would I be killing your presentation?
Well,
okay, I know
you can try. Okay, maybe not. Let's do without it. Okay, so now that the filter is running, well, actually it's run almost to the end. Of course, I mean, the demo here is pretty static because once we've caught up with history, everything stops. On a live feed, everything will start growing over and over again. One of the things I can do on the filter is that I can launch the shut-in identification process. Again, here I do everything manually, but in real life, this would be triggered automatically. And you see here a number of shut-ins identified, which are highlighted with some gray bands, which could be edited if you don't like the finding. Once again, as the data grows, this would keep on going. I will use the shut-in to create some corrected production. So if I go to my production here, I can say I want to make sure that the rates are 0 within the shut-in. And I can also, on the fly, put some simplification. So let's say 10% simplification, so we see it on all rates. So we will get the corrected production. And now that we have this production, so we can compare it with the original one, that's one way to do it. I could build actually a plot, user plot, and drag and drop. So for instance, the oil production before, the oil production after, just to highlight the differences between them. What I can do also is that if I return to my shut-in channel, now that I have a corrected production, you see at the top that there is a view log option. So actually, when I select this view log option, what it triggers is a dialogue between the KAPPA-Automate frontend and the Sapphire instance, which is sitting on the backend. And it asks Sapphire to create on the fly a document with the relevant data for this shut-in, and to extract, basically to compute the superposition function and to extract the log. So I can navigate through the log. We are currently missing the highlight of which log we are, or which shut-in we are currently seeing, but that's work in progress. So that's let's say one of the new workflow within KAPPA-Automate. Let me go back to this, to the well here. And one other thing I can do is upload some analysis documents. So I will upload two of them. I will upload a Sapphire document. Sorry, I thought I had pressed the option, but I did not. So let's start with the Sapphire one. So this is a Sapphire document, and actually when I select this document in KAPPA-Automate, I see, so I have several options here. I can see the log plot. And when I see this, it's actually the KAPPA-Automate front end asking Sapphire to open the document and to give the channel. So it's not an image. It is the real thing. It is the actual channels together with a model if there is a model. Another way to view the content of this document is simply to view the results. And so what we get here is the, let's say, the results encapsulated within the document, displayed in a nice readable way within the UI. So we can do the same with a Topaz file, for instance. So let me take this one. And with this Topaz document, so again, we can see the results. We can see the log. We see that there has been a model. You see at the top a drop list for the analysis. So I could navigate through the analysis if there were several. But most importantly, because I have this analysis and this Topaz document, now I can trigger the virtual production workflow I mentioned before. So if I select virtual production, I can select a name for the output, an analysis, there is only one, and which pressure is going to be the input to the process. So here I select the filter I created before. And so if I create this element, you see a new node in my tree. And under this node, we see that an oil rate has been computed. If the analysis was multi-phase, I would get multi-phase rates. And again, this will progress from now on as the pressure is growing on the server. Okay, so that's the virtual meter workflow that we discussed before. Let me move now to the illustration of the functions and the task. So I will move one level higher inside KAPPA-Automate, and I'm now in, let's say, the part of the UI where you can extend the functionalities within the system. So the first section is the function. So we have some built-in ones. I mean, currently there is only a simple GOR, and I will redo the same, but manually. So I will create something that I will call a GOR. Well, let's take GOR function OA, which I had typed in previously. The formula, so just let's say QG over QO. And if I press parse, so each variable that has been identified can be set to be either a data set or a constant. So if I say data set, I can select the type. So this is gas rate surface in cubic feet per day. And QO is an oil rate surface in barrel per day. The output is gas liquid ratio. Gas liquid ratio, yes, I will find it.
Gas oil ratio.
Yeah, sorry, gas oil ratio. Well, okay, thank you, Vincent. So in cubic feet per barrel, so that's fine. I can accept this function. If I move two levels down, you will see here the section for the user task. So we have some built-in ones. Actually, the corrective production and the shut-in identification are built-in user tasks, but that's where you would create your own. So I will do so and create a GOR task. Let's call it this. Publisher, we don't care. Event key, so let's say GOR. So whenever a computation is triggered, an event GOR will be sent on the bus. And then I put some description. I then need to define the parameters, and to do so, I need to use some special markup language, which is called the YAML. So I have a file prepared. I mean, the name is daunting, but actually the content is pretty readable here. If I paste it there, you see that all it says is that I have two inputs, a gas gauge, which is a data set, it's mandatory, it's gas rate surface, it's by step. Same thing for the oil gauge, and then a definition of the output. I could insert some, let's say, dynamic parameter transformation or code, or let's say code to validate the data. I will keep it here. And then I can go to enter the script itself. So here again, I have a script all made up. I have two actually, one in C#, one in Python, but I will use the C# one here, and we'll see Python in the next demo. So that's my C# code. Let me just take it and paste it there. So, well, the code sounds a bit long for doing a simple division, but there is actually validation of the input, treatment of the absent value, and so forth. So this is basically, let's say, my GOR function. So I can, again, validate it here. And if I'm happy with it, I can create the task. So if I return to the field I was in before, you remember that we had some production under this well. We had, let's say, a basic production and a corrected production. So here I can invoke both the function and the task. So for the function, if I select the GOR function OA that I just created, you see that the binding was done automatically on the first instance of data types with the right, or data with the right type. I can create the function and see the results. Let me just refresh. Did I don't know if I missed a step here. Okay, that's my result. So that the function, again, has been computed for the historical data and will progress for anything that comes in later. I can do the same with the task. So if I go to the task creation, select the task I just created, apply the binding, I can here get a preview in a little screen before launching the task. And again, as before, this will keep on growing as the data is progressing. So that's for function and task. The next thing I will illustrate is the use of the Python SDK. So here I will move to a field, which is this one. So on this field, I have not much. I have a well, and under this well, I have two Sapphire documents, one called MR and the other one called BR, which both have a bunch of shut-in extracted. So what I will do now is I will call this is my Python development environment, which is, I mean, something called PyCharm here. And I'm looking now at a Python script, which is implemented this, let's say, a proof of concept one about infinite acting radial flow detection. So you see at the beginning of the script, so we are importing the KAPPA SDK, and then we start, let's say, doing some meaningful stuff here. We are connecting to the KAPPA server I'm connected to, which is our production server, through its IP address. And then essentially what we will do is that we are specifying a particular field, a particular well, and a particular document. And so that's the one I was just looking at now that you see there. And so what the script does is basically get the document from KAPPA-AUTOMATE, ask the Sapphire on the backend to open this document to provide the results within the document, to provide the log. Then we do the infinite acting radial flow determination, computation, and then we write back the results. So let me just launch the script, and this will be, let's say, more visible. So as the script is running, we will see some, let's say, the steps commented on the bottom. So you see, we read the field, we get the document, we get the log. And if I activate the plots here, sorry, we will see the log plot that was replicated within the Python code using matplotlib. We see the stabilization level that were identified by the algorithm here. And we see, again, within matplotlib, here, permeability versus time and skin versus time. So those two channels have been written back to KAPPA-AUTOMATE. So if I go back to my field here, we don't see them yet because I need to refresh the UI. And when I refresh, you will see a gauge folder under the well. And now we see this permeability versus time. I mean, the points are very thin here. We don't see them very well. And skin versus time plot, okay? So again, this is a one-shot process here. But of course, after validating such an algorithm, the main interest would be to encapsulate it into a service that will listen to the event on the bus and will be triggered automatically on, let's say, on an event that you select and for a well or all the wells of a particular field. Regarding results and basically exploiting time-lapse results, there is, let's say, another thing I can demonstrate here. So let me go back to the top level, and I will create a new field from scratch with a larger number of wells. So let's call it whatever, let's say many wells. And to initialize this field, I will actually load from, let's say, a production file, an IHS 98C file. Now, of course, one of the functionality KAPPA-AUTOMATE will have is to tap into an existing database and to mirror at once the structure of the database with the well properties, the data under the wells, and so on. So here we mimic this with a simple file. So you see on the left a bunch of wells that were created, each of them with some production below them and so on. What we can see also, if I move to this view, which is what we call the flat browser, is that you can see a flat list of the wells with whatever property was brought from the database. So we see that we had coordinates, bottom hole, latitude, longitude, and same thing for, let's say, surface, latitude, longitude, some field name, and so forth. This view actually can be organized in any way you want. So for instance, I could say I want to see first, well, let's say operator name, and then I go by field name. If I take field name here, so everything will be reorganized here by whatever let's say, hierarchy you select. So let's return to the tree here. And what I will show here is how we could essentially exploit some of the functionalities of the platform if we have a time-lapse analysis under a particular well. So those time-lapse analyses could be provided by the user, or they could be the result of some automated analysis like the incremental PTA workflow I showed before. So here I will select two particular wells, and under each well I will upload some analysis document. So I will take the first one here, GPC Panam 2H, and under this well I will upload a first analysis, so PTA 1. That's what the, let's say, the model match looks like. And if I look here, I see that I have a skin of 0 for this particular analysis. I'll upload a second one, which was done a bit later in time. So that's build up number 3 here. Again, the result. So we have a skin of 226 now, and the log plot looks like this. So same model, but rematched on the new shooting. We'll do the same. Okay. One important thing here I was about to miss is that if I look at the well has a list of built-in properties here. You see that it has permeability, productivity index, and skin, and they are without any value right now. If I click on extract results, what's going to happen is that all results contained into the documents available under the wells will be, let's say, used to feed some well property, which is, let's say, a time-based well property. And we will see here the last value. So we see the last skin, which was 2 something, the last permeability, last productivity index. but the whole time series has been selected. Now, right now, it's this is an option where it takes everything, but let's say eventually there will be some UI to let you select which particular results you want to consider or not. So I have done it for one well. I will do it for the second one. So let's go to this well here. And again, I will upload two files, two different ones. So this number 2 file. So here skin is 1, roughly, I mean, close to 1. And then a second one, which is file number 4. Here. Okay, and in this case, I have a skin of 4. So as I did before, on this well, I will extract the results. And you see that for the well, I see the last applicable result, which is my skin of 4. Now, one way to display all those results, especially on a large number of wells, is to do this on a map. So if I go back to the top level, I can create a map. On this map, I will see all the well coordinates. I should see in a second some background, which is OpenStreetView here. I can display, if I want to, for instance, the name, some well stick linking open hole and bottom hole coordinate here. And finally, I can show bubbles. I have three, let's say, three things I can play with: the size of the bubble, the color of the bubble, and possibly a contour. So here I will say that the size reflects the skin. The color reflects the productivity index. And if I say use value through time, then it will give me, let's say, a small slide bar at the bottom where I can navigate in time, and also a drop list where I can see all the relevant time, all the analysis time here. So that's when we had 1 and 0, then it's, let's say, 1 and 2, 2 and 4, well, okay, whatever. So here, this is only shown with 2 wells, but obviously, I mean, if you have something on all the wells, you will see, you will be able to play animation of 3, so combination of 3 results with respect to time. Okay, so that's for the multi-well results. One other thing I can, so let me just make sure I did not forget anything here for the task and multi-well. I think that's all. One of the things I can illustrate now is what we talked about inside the slide, which was how to view and exploit the REST API of all the services on the platform. So to do so, I can come here to this Swagger API. So here at the top, I mean, you see or you don't see that there is an IP address, and then there is a port number. So each service on the platform is at a particular port. So here I'm connected to the field service, the one responsible for creating, updating, and basically manipulating all the elements of the hierarchy inside the field. So the field, the wells, and so forth. So if I scroll down, you see I have a list of all the functions available in this REST API. I can see, for instance, somewhere field command. So this is a command that will let me create a new field. The UI is very slow here. It's due to Swagger itself and the version of Swagger we are using. It's not due to the platform itself. I mean, as you saw, when we are creating field, things go pretty fast. So what I see here is what is expected as an input to the to create a field. So it's a JSON, let's say a JSON payload, if you want, which looks like a little dictionary with basically entities and their values, so a name, reference date, time zone, and so on. So I will, from here, not only can you see what the API looks like, but you can also try it. So if I say try it out, I will have the possibility to enter something and to create a field, let's say calling the field service directly. So again, this is taking a little bit of time here. In the meantime, I will take my Explorer to take the content I want to put in. So here, let's call it, let's say, test OA. Let's say today is July 16th. So let's take this. And I don't know if this, okay, just woke up. So if I paste this inside this space here. Okay, now you see name test08 July 16. So if I say execute, after some time, I should have, let's say, the response of the command. So 201 field was successfully created. And if I return to my top UI, I should see somewhere. So you see here, when before last, test08 July 16. So that's the field that was just created with whatever, let's say, country, reference, coordinate system, and so on we have selected. Okay, so that's an illustration of how you can play with the various API of the services. The one thing before last I will show is if I go to the top level again, here there is a section for monitoring the platform, and actually what we show here is just a simple dashboard with CPU usage or service memory. What we use internally is a tool called Grafana, which will let you build any dashboard you want. So for monitoring the health of the platform, in fact, if I go here, I think I should have something much more comprehensive. So here I'm connecting directly to Grafana to display, let's say, a much more complete dashboard that we had created. I mean, it's probably a bit daunting, but the bottom line is that you can view permanently all the information logged by any of the services of the platform. Last thing I can do, probably before stopping my demo, is connecting to another server, which is this one. This is a server on Azure this time, and not in our premises. Kappa. Okay, I should not speak out the password. So, I mean, it looks the same, obviously, if I just open this field that we had prepared beforehand. This is a field with basically all the stuff that I have created in the previous one when I was doing the demo, with the virtual meter, with the various files under the well, my Topaz documents, my Sapphire document, and so on. The big difference being that now I'm connected to some machine in the cloud. Okay, I think I have covered everything, unless Olivier and Vincent, you think about something I forgot, but I think it's all of it.
No, that's fine.
Okay, so that concludes the demo. Sorry?
Nassim, you take over?
Yes. Thank you very much, gents, for a great presentation. Thank you. And I've got a bunch of questions in here. I have compiled them into a Word document, so I'm going to read them out. Actually, the first question is one that I can actually answer. So the question was, just to share it with everyone, actually, I'll just put my video on, why not? So you can see my face. Can you send the presentation PDF file to the KAPPA Software user clients after the seminar? And the answer to that is yes, we can. We can send you the presentation PDF format, and there will also be a recording of the session that you may request by sending an email to, I don't know if we have our support email address on one of your slides there, Olivier, support@kappaeng.com. I guess I can share that at the end. That's fine. So I'll share the support email address at the end. I'll just share my screen. So yes, you can get that. So Marwan Maru has asked a question on so automation adds more value. So Marwan Maru, I did not get the company name of this gentleman, unfortunately, but the question is, automation adds more value if real-time optimization of production operation systems based on real-time data analytics is enhanced. Value gets mostly added with artificial lift and injection systems optimization. What solutions is KAPPA-Automate looking to provide in this area? So that's the question there.
Well, I mean, if we look at what we are working on right now, I mean, what we have been working in the past 4 years is to build basically the piping. So the world have the platform. And in the, let's say, in the proof of concept, we have essentially been connecting Sapphire, Topaz, and Rubis. And the stories that Olivier has been presenting was around that. So structurally, of course, there is no limitation of what you can do. But let's say in this case, I think that he was dealing with processes that are not that Sapphire, Topaz, and Ruby are not involved with. So notionally, yes. I mean, I don't think that we have anything specific planned for that. Olivier?
Well, I mean, in terms of let's say the engines themselves, I guess we might want to quote or mention Grona.
This is what I thought.
Yeah, I don't know why you did it, but yeah. So we have started to work on let's say 2 new modules for KAPPA-Workstation, which are a nodal package and a surface network. The surface network at first is only let's say available as a complement to Ruby for an implicit coupling within Ruby. But it means that let's say in a year time or so, we will start to have the capability to model the full system from let's say a reservoir to surface. And if we do, I mean, the engine would be a candidate for let's say automatic processing on the platform. I mean, if we want to do this or not.
Sure, thank you, Olivier. And again, yes, I thought this was a good opportunity to obviously mention Glenat, and that's why, yeah, so I thought it was maybe a good question to answer there. A question from Juan Quispe. Sorry if I didn't pronounce your name properly, but he's a production engineering leading the digital oil field initiatives in Peru for Plus Petrol. And this question came twice. It also came from, well, a similar question from Omer Zobairi from Oxy in Oman. And it's basically saying that a key component of KAPPA automation is KAPPA server. Am I missing something? Is this right? And I guess this question was answered with your presentation, Olivier. But you may want to add something to this specific question.
No, of course, the least that we could do was to reproduce the workflow of KAPPA server, and of course, naturally, I mean, automate is a different fish, you know, and certainly for quite a while we will not retire KAPPA server. It will be up to companies that want to move to the next step to update. But naturally, all the capability of KAPPA servers will be integrated in automate. Actually, I guess that we are almost there now.
Great, thank you. Radu Buzea from Cenevis, Calgary in Canada. I love what I see from an automation point of view. From a technical approach, I think our reservoir interpretations are missing a lot on the thermal applications and geomechanical integrations, which have an impact on many of our systems, i.e. unconventional bitumen oil sands, etc. How is KAPPA planning to integrate these into their protocols?
Okay. Yeah, so for some, I mean, for thermal temperature, I mean, we have discussed it briefly in the presentation. We do have some capabilities for integrating thermal modeling within the reservoir models, and I mean it's obviously relevant also for production. So there are things we have now for the reservoir and the well. There will be more coming for let's say other aspect like I mean I think you mentioned bitumen. One of the things we are moving probably into as well is that, so Olivier said that we just released Carbon. In the coming version of Carbon, so not the current one, but the one that we will have next year, we will have, let's say, the ability to predict wax, asphaltene, and so on. And those capabilities will be available also for flow assurance within, let's say, within the nodal and within the network. So all these used in real time within KAPPA-Automate, I think could provide some answer to this kind of situation.
Sure. Thank you. So next question is from Aris Karamessinis from ADNOC. And again, this is a question that was answered during the presentation. You asked it before, but just with the introduction of artificial intelligence and machine learning, will end users be able to create customized workflows within and across KAPPA Suite modules using Python or similar scripts? So again, this was answered. Yeah, go ahead.
Well, I mean, after that, of course, necessarily the ones that will implement, you know, the AI solutions. But you know, as I said before, we are building the piping, which is that any single, down the line, of course, we are still on the POC. but any single action that an engineer is doing right now with the user interface of our application will be accessible through the API. So just it will be a matter of developing these tools, and whether it will be us or others it remains to be seen.
Great. Thank you. Anything you want to add, Olivier, or just that? I guess that answers the question pretty.
No, I think
we can. Yeah. Perfect. So, Leopoldo Sierra. Again, I don't have the company name for this gentleman. Good process, but it is based on the assumption that the quality of the entire data is good. There are many cases where the pressure changes are not related to the reservoir properties. Does your process have any specific step to quality check the data quality?
Well, we have, I think we said before that at the core of the system is the KAPPA server workflow, which includes denoising of the data, I mean, which is the basic, this basic wavelet filter. We have worked on a number of other processes for, I did mention outlier removal. We have worked on trying to train some machine learning algorithm to fill gaps in the data or to spot drastic changes in trend. Right now, I would say we have more explored a possible toolbox than, let's say, come up with a real solution, but it's definitely part of the topics that we want to explore within KAPPA-AUTOMATE.
Okay, great. Thank you, Olivier. And so I will continue, I guess, because I can see the attendance is still very, if you guys are okay with me continuing with questions, we have quite a large attendance. So, yeah. So a question from Véronique Mahou from Silixa in the UK. Great presentation. What is the current status of your DAS processing capability? Thank you.
Well, I can answer with
distributed acoustic sensing, obviously.
It's me right now. Hello, Veronique. Yes, right now for DAS, I mean, we have some prototype code to essentially load and display some DAS image, but we haven't done anything beyond that. We had some, let's say, we had a plan laid out, but so far it has stayed at the level of spec and has not gone any further.
Sure. So Peter Salisbury, again, I don't have the company name. Some of the reservoir simulation specialists are skeptical regarding the value of artificial intelligence. Open bracket, not myself, close bracket. So he doesn't agree with that. But he continues with, however, when you apply artificial intelligence to well test analysis, how do you know for sure that you will achieve the correct answer or solution, I guess, rather than, let's say, 10 possible non-unique solutions? Is there proof by way of a field study that you could post online which illustrates that the correct match has been achieved unequivocally? $1 million question.
Okay,
He
has
been working on this a few years ago. I guess I leave you the privilege.
Well, I guess the first answer, the first part of the answer, I guess, is to say that we don't have right now an AI system that we would trust to do an automatic analysis. We are not aware of an existing one. I mean, there have been a number of publications and research, but let's say one that is currently in use and is, let's say, working 24/7 and providing consistent answer. Unless we missed it, we are not aware of one. I mean, you said you said the magic sentence. You know, a perfect match was obtained, and I guess I mean we have all been trained to get a perfect match in the end. Does it mean it's the response or not? It requires a lot more than this. So getting the match is probably the easy part. Making sure that the answer is the right one. Again, you see that what we have presented is more workflow in which we would see the process with an engineer interpretation and essentially try to automate the replication of that match over and over again. So we are not believing right now in a fully automated interpretation. We will be working on it. We have been working on it, but we don't see the light at the end of the tunnel yet.
Yeah, in fact, in complement, you know, even the basic AI system that we had developed 20 years ago was not given a unique answer. It was giving actually a list of potential models that could fit the data. There is no, as I was actually explaining on the beginning of my presentation, we are not speaking about a system that is aiming at exceeding the capacity of what an interpretation engineer is. And if you have been dealing with real-life witness interpretation, you know that there is no such thing as the final model that is making it all, unless you are interpreting simulated data. So I don't think it's a good, it's a fair attack to AI to just say, okay, well, there is no way we can have that. No, again, AI is just a sophisticated set of algorithms that will allow us to reproduce something that is more than just an optimization. But today, we do not have, let's say, any pretense to replace and to have a system that will give you the answer. What we are aiming at is essentially AI systems that would be told by the engineer, try this model. That would be probably more realistic. But something that out of the blue and regardless of the geology, the geophysics, etc., will take the data and do an analysis is totally unrealistic, and we will not even try to do that.
And may I just say thank God for that, because then it justifies our job in the industry still.
That's not a good reason, but yes, this is a good consequence.
Okay, so there's a question here from David Teague and from Chevron. When displaying PTA results in KAPPA-AUTOMATE, can each analysis file have more than one valid analysis or just one per file? If yes, will there be a pick list?
Yes, like I said, so in the demonstration I made, I was clicking a button and everything was brought in at once. It will be possible to select the ones you want to bring in. Yes, you will have that capability.
Thank you. And I'm going to read a question because some of the Aramco, sorry, I'm on WhatsApp because Aramco did not have access to Zoom with this Q&A. So this is from Bandar Wahabi from the Well Test Division at Saudi Aramco. Does virtual metering use machine learning in creating the rate? Does it use the existing rate? So by that, I'm assuming, does it use pre-existing?
No, well, no, absolutely not. I mean, the virtual meeting is what? We have created, the engineer has created a model. He has done a topaz analysis, for example, and he has a model. And what we do with virtual metering is that when the engineer will, as Olivier did, drag and drop the topaz file onto the well, it will basically take the model that is, or the analysis that is in this file, and then we'll select whatever permanent gauge is being filtered, and essentially will constrain the, let's say, the model, not with the pressure that is on the topaz file, but with the pressure that is coming real time from the virtual gauge. So there is no machine learning here. It is deterministic. We are getting the model selected by the engineer, and just 24/7, the system is simulating, so it's making a sort of allocation, so that if the pressure that you have is the real one, if the model that you have put is the valid one, then this is the rate that is produced by your well. So there is no machine learning. We could imagine machine learning algorithm to do analysis, etc., but this is not what we have been demonstrating.
Sure, and while we're here, because you asked me a couple of questions here, so there's another one on auto-filtration. Is it changing based on the data condition, or does it just apply to the same set on all data as KAPPA server does right now, basically?
So, well, several answers. The auto-filter demonstrated is only the default parameters that you would obtain if you were calling, or let's say, going through the wizard and just praying next. So it is data dependent because the threshold, which is the main driver for the denoising, is data dependent. But it's let's say this is basically the same as executing without a UI. This being said, I should mention that we have done some work on let's say on the denoising. We have implemented a new wavelet algorithm that we will be connected and called wavelet 3. I mean, it's very similar to the second generation, but much more efficient. It's a much more efficient implementation. We have also done something specific for rates, which we had presented before. At least we talked about the idea before, but it's been now implemented. to deal with very noisy rates coming possibly from a multi-phase flow meter. And what we do there is that we don't use wavelet, we just work on the cumulative, filter on the cumulative, and then redifferentiate, keeping, let's say, honoring the cumulative value. So those are, let's say, this is some of the work that we have done. We are still aware that the wavelet denoising as it stands sometimes is still a bit frightening for the users, and they are not really sure what the threshold should be, how it should be adjusted, and so forth. So we still have a number of ideas we would like to explore on this, but so far we have hardly started.
Sure. I've got a few more questions here. It's 3 more. If we're happy to continue, I guess, because we've still got a lot of people in here. So if you guys are happy to answer these, or we can answer by email.
If it's not just the 3 of us online, yes.
It's fine. Not just the 3 of us. We've got a lot of people.
No, I know. I was joking.
Yeah, absolutely. So let's continue. So Cesar Rodriguez, you've got a question there, and this question is, please, could you explain a little more about the Python workflow? How it is used to improve the PTA analysis and estimate reservoir parameters? Cesar Rodriguez, again, I don't have the company name there.
Well, I guess say one way to rephrase it is to say that, like Olivier explained, all the functionalities of Sapphire, all the options in Sapphire, extracting, shutting, making a computation, drawing a line, or whatever, will be options that you can call programmatically from Python. So if you want to implement a particular workflow, now of course this workflow is for you to decide. It's not, let's say, we are going to provide the one corresponding to the proof of concept we are developing. It's our intent to have those, let's say, built in. But then the idea is that through the Python SDK, you can build your own workflow and do absolutely what you want and automate any workflow you want that calls functionalities of Sapphire on your data.
Great, thank you, Olivier. Very clear. Omer Zoberi from Oman, would be good to see time-segmented regression. I guess this is a comment rather than a question. So Omer, I'll email you later about that. There's a comment. I mean, I guess I can say it. So it would be good to see time-segmented regression to identify reservoir well parameters that minimize the difference in the match. This could possibly allow the engineer to see which parameter is paramount. Yeah. So it's just a comment there. So
actually, one of the things we had done, which is very much in line with this, is that so when we started looking at possible ways to refit model, so the incremental PTA workflow where you have something you want to refit it on a new build-up. One thing that works extremely well when you have it is the analysis tools, you know, the diagnostic tools that we have within KAPPA-Workstation that you can set up. If you have the tools for the models you are using, and obviously, I mean, Sapphire has them, then there is a magic button in the log plot which is called reset match that you maybe have tried sometime, and it's quite blunt because it's taking like let's say the first 1.5 log cycle as early time and so forth. But many times it works pretty well at refitting those tools, and from those tools we can then refit the model. So this would be a way of doing this, let's say, time sequence regression. Of course, the big issue is where do you split? I mean, I guess that's the whole difficulty of the PTA analysis, is that to analyze you need to split, but to split you need to analyze, and it's a catch-22 situation, really.
Sure, thank you, Olivier. And one last question, and that's from Anisur Rahman, Saudi Aramco. You have processing and artificial intelligence components of KAPPA-AUTOMATE. In large data of pressure, rate, and temperature, there are sections where these measurements are not consistent. Can you deploy artificial intelligence or machine learning to validate consistency of the entire data set? Can you recreate some data where it is necessary?
I guess, I mean, the consistency has to be, has to come from some kind of model. So either, let's say, a physics-based model, but I guess if we have the model to start with, well, if we have a model that was history matched with time, then we could spot when differences are happening. But differences could be linked to either the model not being applicable anymore or the data being wrong. I mean, either one. We have done things like this with, I think I mentioned it before, with some machine learning algorithm. And this was done in the context of Citrine, where we were trying to spot, for instance, frac heat between wells, or let's say interference between wells. And so we were training a machine learning algorithm to predict rates from pressure. I showed something like this with the feature-based deconvolution also. And then, so if there is a significant change at a point in time, you know that something has happened. But again, so if you trust the model, you can use it to fill the gaps. But if there is a drastic change in trend, I mean, maybe the model is not applicable anymore. So in principle, yes, things can be done, but I guess it has to be done in an intelligent way.
Yeah, we're kind of reluctant about creating data. So again, even though effectively what we have been working on would allow us to detect inconsistency, and therefore if there is no inconsistency because there is a void or whatever, we could effectively fill in the rates when there is no pressure or the pressure when there is no rate. The problem is once you have done that, you know, where will you stop? I guess that it's better, at least we believe that it's better to just get the data we have and match. Let's say whenever we can. But in theory, it would be possible. In practice, I guess we are reluctant to do that.
Perfect. And I'm sorry, there was one that I missed here, and it came from YouTube. And since it will be the only YouTube request, I guess we can that I've had so far, I guess it'd be nice to answer this one. So is Kappa going to use artificial intelligence to optimize well production and the field development? For example, minimum horizontal well length, minimum number of hydraulic fractures required, well spacing, etc.
You're muted, Olivier.
Sorry, yeah.
Okay. First of all, you may not need necessarily artificial intelligence to do that. I mean, you can have
sensitivities.
Sequential. As I said, automation is not systematically artificial intelligence. Artificial intelligence is just one of the tools with data analytics and with whatever, let's say, to try this sort of thing. So what you do could be actually a trial and error. It could be a Monte Carlo. It could be, there are several ways where you could effectively run scenarios and end up with an optimal position. Again, artificial intelligence is not the magic wand that is going to solve everything. We believe that most of the workflows that will be implemented will be using more, let's say, traditional tools and still be very efficient.
Okay, that's great. I think we've answered all the questions, pretty much all of them. Any questions that maybe I missed, we can always send you an email. And of course, we can always email support@kappaeng.com, and that would be for the recording and for any questions that you may have. I can maybe just type the address on a slide here on my screen. And yeah, I mean, thank you very much, gentlemen. Great presentation. And at this point, let me read just one message that came into the chat, actually. Thank you very much. So this came from Roberto Nieves. He says, thank you very much for your excellent presentation. You're definitely at the top of technology in the area of pressure analysis and production. Congratulations and success today, tomorrow, and always. So a nice message to read at the end that came on the chat. So yeah, thanks again, gentlemen. Thank you. I'm just going to share my screen, and I just make sure I don't share the screen there. And just to put the email address where, for whoever's left here, if you wish to request the recording. So share. So Vincent, I'm trying to figure out how I share my screen on the webinar because I've never done it before.
Support@kappa-AUTOMATE, this should be okay.
Yes, support@KAPPA-ENG.com. Hopefully, yeah, everyone can. I don't need to write it down yet. Okay, great. So that ends the session. I'll pass it over to you, gentlemen, if you want to say anything at the end. And that's
absolutely not. I mean, we are at saturation point now. But okay, so thanks a lot, and see you next time.
Thank you very much. Goodbye. Bye.
Thank you.
Bye, Vincent.
Bye.